body is under free fall, if it's dropped from an altitude and allowed to move under the influence of its own weight, under the influence of its own weight. The funny thing is that when bodies are dropped, they will all be attracted towards the Earth's surface. They will all move with the same acceleration. And this means that if bodies of different masses are dropped from a given altitude, they will all fall at the same rate and they will reach the ground at the same time. However, practically, it may not come out due to other factors. For example, if you were to drop bodies of different dimensions, due to air resistance, due to upthrust, these bodies may fail to reach the ground at the same time. However, if they were dropped in a vacuum, they would all travel the same distance in the same time, and they would land on the ground at the same time. So all bodies would be accelerating at the same acceleration due to gravity. In order to handle these challenges, we shall be using the equations of uniformly accelerated motion. So in the previous lesson, we looked at the three equations. So we shall also be using the same equations when it comes to the calculations. So what you have to note are attracted towards center, and they will all move with the same acceleration, with the same acceleration g, i.e. g equals 9.81. on or for a body close to the Earth's surface. So bodies will all be attracted and they will fall with the same acceleration, and that is the acceleration due to gravity. This value of g approximates to 9.81 if bodies are close to the Earth's surface. However, as you move away from the Earth's surface, the value of g changes. But for simplicity, we shall be looking at bodies dropped close to the Earth's surface. So the equations that shall be used in calculating the various parameters, they are going to be the same as those equations of uniformly accelerated motion. To calculate the various parameters, we use the equations of uniformly accelerated motion. So let's look at example. The velocity with which it hits the ground. So this is going to be our first example. A body is dropped from an altitude. When we talk of an altitude, it's going to be the distance measured from the Earth's surface for a body. So a body is dropped from an altitude of 120 meters. Calculate Roman 1, the time taken to land on the ground. Roman 2, the velocity with which it hits the ground. So whenever you are given a question, you have to first read through and understand it properly. So in this case, if a body is dropped from an altitude, it means that its initial velocity is 0. So you shall write the information given. U is equal to 0. H is equal to 120 meters. So that is the information given. Now the question requires to calculate. You want us to calculate Roman 1, the time, I can call it maybe T1, and Roman 2, the velocity V is also required. Now from the equations of motion, so from V equals U plus AT, now we are going to substitute the value of A to be that due to gravity. Therefore this equation will now become V equals U plus GT. Likewise the other equations, the second equation will become S is equal to UT plus a half GT squared. And lastly, the third one, it will become V squared equals U squared plus 2GS. Now these are the equations that we are going to use. The question will dictate which equation to use. So in the first case, we want to find the time. We are given the initial velocity and also the height. Therefore, the equation which we are going to use in this case is going to be the second equation. So, using the second equation, using equation 2, we want to find the time. We shall have AC, we shall take it as 120. Our initial U was a 0, so 0 times T will get a 0 plus a half times 9.81 T squared. Since we are now looking for T, we are going to make our T the subject. So when you cross multiply, we shall get 120 times a 2 is equal to 9.81 T squared. So T1 is equal to the square root of 24.46. So T1 is equal to root 4.95 seconds. So that will be the time taken by that body to drop through a height. Calculate the velocity with which that body will hit the ground. So you have to think of an equation which has velocity in it. Now, when you look at our three equations, the first one and the second and the third can all be used to calculate the final velocity. However, if we are to use the first one, then the time which we shall substitute will be the time we've got here. However, if the time you've got here is wrong, then the chances are that even Roman 2 is wrong. So I'm going to use the third equation so that I will rely on the value of S that was given, because that one I'm 100% sure that it's correct. So from the third, equal to U squared plus 2GS. So when the body hits the ground, if you have V squared, this is a 9.81 times, you will have covered that distance. 100 is equal to 2 times 9.81 times 120. So this is 23. 54.4. There the square root of 2354.4. So we shall get our V 0.5 meters per second. So that is the velocity with which the body will hit the ground. The body is dropped from the top of a building the body passes past a window of height 6 meters in 0.2 seconds. Calculate Roman 1 the height of the building above the window. Roman 2 the velocity the body moves with at the instant of reaching the window. From the top of a building, the body passes past a window of height 6 meters in 0.2 seconds. Calculate Roman 1 the height of the building above the window. Roman 2 the velocity the body moves with at the instant of reaching the window. So that is our second example. So after reading through the question, you come up our building. And maybe this is our window. We are told that the width or the height of the window in this case is given to be 60 meters. So the body is dropped from the top of the building. So this body, it will not refuse, it will definitely fall. So at this instant here, I'm going to assume that it will be moving with velocity v1, and then after passing the window, it will have attained the velocity v2. So this is the direction in which the body is falling. And now the question requires us to obtain the height above the window. So the question requires us to find the value of h. So physics may be somehow interesting just by measuring the speed with which the body passes the window, and also knowing the distance and the time taken, we can use that information to calculate the height above, meaning that there is no need of us to use maybe a tape measure at that instant to obtain the height. However, this requires you to use equation window and the time taken. So we are going now to form two equations having the given information. So I'm going to call this level A, I'm going to call this level B. So consider the body at A. So the equation which I'm going to use, so from plus a half gt squared. So if the body takes the time t2, if the body takes the time t1 to follow through distance h as shown in the figure, then we shall say, or we shall have h. Remember, it was just dropped. This here is a 0. H equals a half g t1 squared. So I'm going to call that my first equation. So consider the body at level B. So consider the body at level B. Again, exploiting the same equation. So the height through which it will have dropped is going to be equal to h plus 6. So I'm going to have h plus 6 is equal to a half g, and the time is going to be equal to, remember we are told that it takes 0.2 seconds to fall from here up to there. So I'm going to get the time from here up there, then I add all the 0.2 seconds. So it's going to be t1 plus 0.2 seconds squared. So this is now our second equation. Now when you look at these two equations, we are having two unknowns, the h and the t. So we are going to solve these two simultaneously. So I'm going to apply the knowledge of solving simultaneous equations to see that we get the value of h. If we don't know the value of t, getting the value of h will be somehow a bit hard. So I can first find the value of t1 and then use one of the equations to get the value of h. So I'm going to substitute this expression for h, solve for t1. So after getting the value of t1, I substitute in any of these equations to get the corresponding value of h. From equation 1 and 2, so we shall have our h is a half g t1 squared plus 6. This is equal to a half g. So I'm going to expand this. We shall get t1 squared plus 2 times 0.2 t1 plus 0.2 squared. So we shall get a half g t1 squared plus 6 is equal to a half g t1 squared. Multiply this, you will get plus this 2 will cancel with that 2. 0.2 g t1 plus 0.2 squared divided by this 2 times the g. So this will cancel with that. So we shall have now our 6 is equal to 0.2 times 9.81 is 1.96, 1.962 T1 plus 0.04 times 9.81 divided by 2, 0.1962. So 1.962 T1 is equal to 6 minus 0. And when you try to make T1 the subject, you will get 6. 5.8038 divided by 1.962. So you get T1 is equal to 0.962. So we are getting 2.9580 seconds. So it means that the body took time of 2.958 to fall from this point to that point. Now, in order to get the value of g is 9.81 times the time squared. 2.958 this squared. So you will get your h to 9.81 2.958 squared. So it is 42.92 meters above the window. So that is the value of h. So Roman 2 requires us to find V1. The instantaneous velocity when this body has just reached the window. So from V is equal to U plus GT V1 will equal to 0 plus G T1, where T1 is the time taken. So in this case, V1 will equal to 9.81 times T1, which is 2.958. So V1 will equal to 29 meters per second. So there are quite many ways how they can trick questions. They can bring the same question, but instead of giving you the time, they may give you the instantaneous velocity with which the body. Again, from that, provided you apply the proper equations, you can get the answer. So this is an example that exploits the knowledge of free fall, and we have seen that we can use that knowledge to calculate the height of a building just by measuring the time taken by the body to pass or to cover a certain distance. So you can estimate the height of the building just by measuring the time taken for this body to drop through a given or a known height. So we are now going to look at vertical projection. A body is projected vertically upwards if it's given an initial velocity and it is allowed to move under the influence of its own weight. So in this case, the body will move, it will reach a certain point, and then it will come back. So what causes the body to come back? It's going to be the influence of its own weight, which acts towards the Earth's surface. So we shall be applying the equations of uniformly accelerated motion. However, the acceleration which we shall be using is going to be equal to negative g, which is the acceleration to gravity. So when a body is given an initial velocity, it will continue moving along the vertical up to when it covers the maximum height. So the body will then drop. So we apply the equations of motion equal to negative g, i.e. we shall have v equals u minus gt, s is equal to ut minus a half gt squared, and this squared will equal to u squared minus 2gs, where s is the vertical displacement. So these three equations example, a body is projected vertically upwards velocity u. Write down an expression in terms of u and g for the Roman 1 maximum height reached to time taken to reach maximum height three time taken for the body to return to its point of projection. A body is projected vertically upwards with an initial velocity u. Write down an expression in terms of u and g for the Roman 1 maximum height reached, Roman 2 time taken to reach maximum height, Roman 3 time taken for the body to return to its point of projection. Therefore, the equation which we have to think of has to have a component of calculating the displacement. However, the condition maximum height, its final velocity must be equal to 0. So from v squared is equal to u squared minus 2gs. So for maximum height, hm, v must be equal to 0. So therefore 0 is equal to u squared minus twice g. So where there is s, I'm going to put hm. So when I make this the subject, we shall get hm is equal to u squared divided by 2g. So that would be the expression for the maximum height. Roman 2 time taken for the body to reach or to return. So the time taken for the body to reach maximum height. Let Tm be the time taken for the body to reach maximum height. For the body to reach maximum height. V equals u minus gt. So when t equals tm, then v must be equal to 0. Therefore 0 is u minus g tm. And when you make tm the subject, you will get tm is equal to u divided by g. So that would be the expression for the time taken for the body projected vertically upwards with an initial velocity u to reach maximum height. Lastly, Roman 3 Roman 3, if this was our point of projection, the body goes and then it returns. We have so far obtained this value HM. We have also obtained this value here when the velocity v is 0. Now they want us to find the time it takes this body to come back to its initial point of projection. Now we can apply symmetry. The time taken by this body to move from here up to this point is also the same time it will take to drop from this point back to the point of projection. So by multiplying, let t be the time taken. So that t can be obtained from multiplying the 2, so that we can get 2u out of g, i.e. tf is equal to 2u all from s is equal to ut minus a half gt squared. When the body returns, to the point of projection, the displacement s is equal to 0, and therefore our t must be equal to tf. When you substitute, therefore 0 is equal to u tf minus a half gtf squared. So this is the same as tf bracket u minus g out of 2 tf. Now when you apply the zero theorem, you shall have either tf is equal to 0, and that is the time when the body was projected, or u minus g tf out of 2 is equal to 0. And when you make tf the subject, you will then get your tf equals 2u, and that is the time when the body has come back to the point of projection. So what you have to recall here, that when the body is projected vertically upwards, we shall be taking the acceleration negative. By putting that negative, the equation will cater for the rest. And also try to see how we can handle such a challenge. A stone is thrown vertically upwards with a speed of 20 meters per second from a point at a height h meters above ground level. If the stone hits the ground 5 seconds later, find h. So stone, so if this is our ground, this is maybe, so the stone is somewhere here, it is projected vertically upwards with an initial speed u, which is equal to 20 meters per second. So this stone, what it will do, it will move, it will reach a certain point, then it will come back and it will now hit the ground. So if at this point t equals 0, we are told that it hits the ground when the time t is equal to 5 seconds, and now they want us to use the given information to calculate the value of h. So that's our diagram. Remember, the information that is given, it's the one which dictates which equation to use. If we have been given time, we have been given h and the initial velocity, we are now going to exploit the second equation. So we shall have from s is equal to ut minus a half g t squared. Now this h here, if you look at this critically, it is below the point of projection. So if h is below the point of projection, we shall take that displacement to be negative. So we shall have negative h is equal to u is positive, which is 20, times the time t which is given 5 seconds, minus a half times 9.81 times 5 squared. So you don't have to split this to first find when the body reaches up. Just by putting this negative h, the equation will be able to do everything for you. So 20 times 5, that is 100 minus 0.665. So your negative h is equal to negative 22.625, implying that now my h is 22.625 meters. We've been calculating the height below the point of projection. Now let's also look at another example. It may have other features which we need to know. So a stone is projected vertically upwards from ground level at a speed of 20 meters per second. Find how long after projection the stone is at a height of 19 meters above the ground. Part A for the first time, part B for the second time, part C for how long is the stone at least 19 meters below the ground level. Reach a certain point and then it will also come back at the same point of projection. The initial speed u of projection is given to be 20 meters per second. Find the stone is at a height of 19 meters. So if this is my 19 meters, so they want us to find the time. So if at this point I take my t to be equal to 0, so I'm now going to find the time. I can take that to be equal to t1 when h equals 19 meters. It will be at this instant when the body is at this point. Then part B for the second time, it will be when the body is now on its way back and it's at that point. So during these two instances, the body will be at a vertical distance of 19 meters below the ground. In the first case, it is moving up, and in the second case, it is moving down. So we are now going to apply the second equation to see how we can make it produce those two values of t. So from s is equal to ut minus a half ut squared. So now 19 is equal to the initial, which is 20, t minus a half g t squared. So in this case, t is going to be the t1. Actually, now that is a quadratic equation in t, meaning that it's going to give us two values of t. So since the majority have got a phobia of fractions, so I'm going to begin by multiplying through a 2. So we shall have 38 is equal to, this is 40, t1 minus 9.81 t1 squared. This is the same as 9.81 t1 squared minus 40 t1 plus 38 is equal to 0. So this one is now a quadratic equation in t, and we are now going to use the general formula for calculating for t. So in that case, t1 will be equal to negative b, since this is now our b, so we shall have 40 plus or minus the square root of 40 squared minus 4 times 9.81 times 38 divided by 2a. That's our general formula for any quadratic equation. So in this case, we shall have t1 is equal to 40 plus or minus 0.43, and this is 19.62. So now this equation is going to give us two values of t. So we shall have the first value, if I'm to call it t1. I'm going to take the minus, so it is 40 minus 10.43 divided by 19.62. So it's giving me 1.5 seconds. That's when I use the minus. And therefore the T2 is when I use the plus. And 2.57 seconds. So what you have to observe here is that T1 is at this instant when the body is on its way up. So that's when the T1. Then in T2 is when the body is at this instant coming downwards at the same vertical displacement from the ground. So those are when the body is at a height of 19 meters above the ground. The T2 is for part B, when the body is at this height for the second time. Then part C, for how long is the stone at least 19 meters below the ground level. They want us to find the 19 meters above the ground. So in this case, the time taken to move from here up to there is the same time taken to move from here up to there. So this interval is when the stone is below, and therefore the required time we are going to multiply it 1 times 2. So Roman 3. So the time required is equal to twice T1 1.5, and this one will give us 3 seconds. So if they had asked us the time when it is above, then it would be T2 minus T1 to get the time taken to move from here up to there. But for this question, they wanted the time when it is below that altitude of 19 meters. The time when a body is at a given vertical displacement from the point of projection, and we have seen that there are 2 times when it is at that altitude. That is when it is going upwards and also when it is moving downwards. So as long from the same point at the same time, one vertically upwards with speed 30 meters per second, and the other vertically downwards at 30 meters per second. Find how far apart the stones are after 3 seconds. Now when you look at this question, it is combining 2 bodies. One is projected vertically upwards and another one is projected vertically downwards. Now if this was the starting point, so one will move up, another one will move down. So we have been given that the initial here is 30, and also for this one its initial. Since they are the same, I'm going to use the same 30 meters per second. Now they want to find the distance between the 2 stones after 3 seconds. So after 3 seconds, remember this will have moved through time interval of 3 seconds. Also this one will have moved through a time interval of 3 seconds. So if this is at that point, even this one will be at a certain point below. So if I'm call this body A, let this be body B. If this one has moved through a vertical displacement A minus a half gt squared, so we shall have h is equal to u is 30 times the time, which is 3 seconds, minus a half times 9.81 times 3 squared. So we shall get h is equal to 30 times 3 this is 45.5 meters. So for body B, so from symmetry, from S is equal to UT plus a half GT squared. So we shall have H is equal to, so this is 30 times the time plus a half 9.81 times 30 times 3 squared. So actually it's quite interesting. You might have thought that they will have moved through the same displacements, but the calculations are giving us something different. Therefore h is equal to 5 times 3, that is our 90, plus this is 44.145. Therefore h (154). So now the distance required, since they are not the same, so if this may be h prime, now the required distance is this distance, which is y. So that is y equal to h1 h plus h prime. So you will get, so in the first case it is 45.855. The second case it is 134.145. So you get y as 180 meters. Ascending at constant velocity of 6 meters per second, drops an orange at t equals 0. Calculate Roman 1 the distance between the lady and the orange at t equals 60 seconds. Roman 2, calculate the velocity of the orange relative to the lady at t equals 60 seconds. Now what makes physics interesting is that they can set a question cutting across different topics. Actually, a good question is the one which cuts across many topics as possible. Now in this case, this question will require you at least to have the knowledge for a body moving at constant velocity and that of a body which is projected vertically upwards. Sometimes the question may not be straightforward, and that's what makes it different in order to test the potential to interpret the question. So there is no need of us to draw a real lift. So I can just use a point t equals 0. So if this is, so I can take this, let this be the point at t equals 0 when the lady drops the orange. Now when the lady drops the orange will now turn into a body that has been projected vertically upwards with the initial speed of 60 meters per second, the speed with which the lady was also moving. So as the lady continues moving, also the orange we have, so let me assume that maybe at t. So we are not certain whether at t equals 6 seconds this orange will be moving up or down. However, the calculation will bring it out properly. So in this case, I'm going to assume that the orange was on its way downwards. So if this is at t equals 60 seconds, maybe I can take also this to be t. So I'm going to take now the lady to be at this point. So the lady is moving at the same velocity as that of the lift. So if I'm calling this v, v is 6 meters per second. So at this instant, if this is my orange, I can see that it will be moving maybe with the velocity which I may call v2, so that it's different from v. So the distance moved by the lady, I'm going to call it y1, and the distance moved by the orange, I'm going to call it y2. So the required distance is going to be the sum of the two. So if h is the required distance, then h is the summation of the magnitude of the two. So calculate and the orange. So in order to get that distance, we are going to find the values of y1 and y2. So let y1 be the distance moved by the lady. Moved by the lady from the instant she dropped the orange, from the instant she dropped the orange, i.e. t equals 0. Now since the lift is moving at constant velocity, so we shall have y1 is equal to v times t. So distance is equal to speed times time if speed is constant. Therefore, y1 is equal to 60 times the time, which is also 6, and this is equal to 36 meters. So y1 is equal to. So now let's look at the orange. So let y2 be the distance in fact, since we are of the orange from the instant it's dropped, from the instant when it was dropped. Now, as soon as this orange leaves the hands of the lady, it will now be as if it is under free fall. So the acceleration due to gravity will start acting on it. However, its initial velocity is going to be the same as that at which the lady was moving. So we shall have u is equal to 60 meters per second. Now even t, they have given t as 60 seconds. So from S, is equal to ut minus a half gt squared. So now my y2 is equal to u, which is 60 times 60 minus a half times 9.81 times 60 squared. So using your calculator, be able to get the numerical value of y2. So we are having so I'm getting negative 140.580 meters. 6 times 6.2. Now the impact of that negative is that the orange will now be below the point of projection. Otherwise, if I had got y2 as a positive, then it would mean that this there has not yet reached its maximum height. But now the negative, it means that it is below the point of projection. So the required distance, so the distance h, in this case, we now take the magnitude. So it's going to be equal to y1 plus y2, so 36 plus 140.58. So you will get h is equal to 176.580 meters. Remember, the negative is just an indicator that the body is below its point of projection. So, range relative to the lady at t equals 60 seconds. The velocity of the orange, that is v2, relative to the lady. So if this is v1, so it will be, which is equal to v2 minus v1. So v1 is already known, so we are now having a task of finding v2. Now, since they are all moving along the same straight line, so we shall just add as if we are adding scalar quantities. So let's find v2. So from v is equal to u minus gt. So we shall have now our v2 is equal to u, which is a 60 minus 9.81 times the 6, which is the 10. So we shall have our v2 equal to 60 plus 9.81. So negative 52.86 meters per second. The negative is an indicator that the body is moving downwards, so we shall be taking the velocity to be negative. So by substituting in the equation for calculating the relative velocity of the orange relative to the lady, so v2 is negative 52.86 minus v1, which is the 6. When you simplify, get 58 negative 58.86 meters per second as our answer. Is projected vertically upwards with a velocity of u meters per second, and after t seconds another particle is projected upwards from the same point and with the same initial velocity. Prove that the particles will meet after a lapse of from the instant of projection of the first particle. So we are now having a task of deriving this given expression. However, we are going to apply what all along we've been using. So we begin by sketching the challenge. So using a simple line, represent the motion of our body. So we have our first body is projected, so it will move vertically upwards. Then after a time t, another body will also be projected. Now if those two bodies are to intercept, then the second body will be moving upwards as the first one is on its way downwards. So in this case, if this is our second body moving upwards, they do with speed, I'm going to call V2. Then the other second body will be moving downward at speed, which I may call V1. So another condition is that they will be at the same altitude, which is h. So now, using those two conditions, I'm going to rewrite the two equations that will enable us to solve for the required expression. So for simplicity, I'm going to call the first body A, and I'm going to call the second body B. So let T1 be the time taken for body to cover the vertical displacement h, vertical displacement h. So this is vertical displacement. I'm looking at this body A. Then the general equation governing its motion shall have from S equals ut minus a half gt squared. For body A, now my S is going to be equal to h u. Now the time is my T1 minus a half g T1 squared. Call that equation 1. We are now going to look at body B. So for body B, again using the same equation, you should have moved through the same vertical displacement h. So we shall have h, since it was also projected with the same initial speed, we are going to also have the same value of u. Now the time, remember, body B was projected after t seconds, meaning that for it, it will have used less time compared to T1. So we shall have T1 minus that time lag minus a half g bracket t1 minus t squared, and that is our second equation. We are now going to play around with those two equations to see that we eliminate what we assumed. So we are going to eliminate the h, and then we find, or we make t1 the subject. So combining equation 1 and 2, combining equation 1 and 2, so I'm going to equate the 2. So we shall have ut1 minus a half g t1 squared is equal to u bracket t1 minus t minus a half g bracket t1 minus t squared. So we are now having a task of making t1 the subject. So opening the brackets, we shall have, open the brackets, u t1 minus a half g t1 squared is equal to u t1 minus ut minus a half g. Now this one, t1 squared plus twice t1t. Since it is a minus, this can't be plus, minus, then plus t squared. ut1, this one will cancel with that ut1. So we shall have negative a half g t1 squared is equal to negative ut minus a half g t1 squared plus the 2 will cancel with that g t1t minus a half g t squared. So this minus a half will cancel with that. So we are now left with the ut. This ut, when it crosses the equal sign, that's why the sign has changed. A half g t squared is equal to g t1t. So when you correct like terms, I can pull out the t into u plus g t out of 2 is equal to g t1t. So this t will cancel with that t. Now when you try to make t1 the subject, I'm going to divide the g throughout. So we shall have our t1 is equal to bracket u divided by g plus, so this g will cancel with that, t divided by 2. And when you try to rearrange, so all this is the same as t1 is equal to t out of 2 plus u out of g seconds. So that's the final expression which is required. The particle is projected vertically upwards with a velocity of u meters per second, and after an interval of t seconds, another particle is projected upwards from the same point and with the same initial velocity. Prove that they will meet at a height of given in the expression. So this challenge is similar to the previous example. So if this is our point of projection, and call it O. So once the body is projected with the speed u, so it will move upwards. Let me suggest that at it stops somewhere. It will at this point moving downwards. So after an interval of t seconds, another particle is projected upwards from the same point. So another particle is projected upwards from the same point. So it will come, and maybe after some time t, it will be at that point. Prove that they will meet at a height. So if this is my height h, where they will meet, they want us to show that that h is equal to 4u squared minus g squared t squared, the whole of it over 8g. So if this is my first tip, if it takes time t1 to reach here, so the state of the particle here, I'm going to write h, whereby it can be the displacement. So if it's moving with the velocity v2, I can call it v2, and if it has taken time t2, I can call this t2 there. Now for the first one, so if this is a, for the second one, if this is b, it will be at a height h, moving with velocity which I can call v1, and the time it will have taken, it's going to be t2 minus the lag, t2 minus t. And now we are going to use the given information to prove that expression. So let A be the first body and let B be the second body. So considering the first body, so for the first body, from S is equal to ut minus a half gt squared, we are going to have our h is equal to u t2 minus a half g t2 squared. That's our first equation. So for the second body, we are going to have again, if they meet at the same point, so h will equal to u. So this is t2 minus t minus a half g bracket t2 minus t squared. Now they want us to prove that the value of h is going to be equal to the given expression. Now when you look at these two, we are now having a task.